Hi friends, welcome back to Edupedia World. In our previous lecture, we studied about a couple and about the equilibrium of a body. In today's lecture, we'll see the principle of moment, which deals with the equilibrium of a body. It's a mathematical treatment, and then we'll solve certain numericals to understand the principle of moment better. Let us begin with our lecture today. In the last part of our previous lecture, we saw the conditions of equilibrium. The first was that the net force acting on the body should be zero. The second was that the sum of moments of all the forces acting on the body should be zero. Now, if a body is pivoted at a point, then the first condition is met default. That is, the net force acting on the body will be zero. Why is it so? Because the pivot will provide the reaction force which will counter the external applied force. But for the body to have complete equilibrium, the rotational forces should sum up to zero too. What do I mean? I mean that the second criteria, that is the sum of the moments of forces of all the forces on the body, should be zero. This is exactly what the principle of moment states. So let us begin with principle of moments. What it says is that if the algebraic sum of moment of all the forces on a body is zero, remember that this should be zero about the pivot, then the body is in equilibrium, From this we see that for equilibrium the sum of moments should be zero. Sounds quite simple. But what exactly does algebraic sum of moment imply? What this implies, the term algebraic, what this implies that we need to take into account whether the moment due to a particular force is clockwise or is it anti-clockwise. We have to take into account the sign of moment due to each individual force, and when we add the moment for each forces, taking into account its sign or whether it is clockwise or anti-clockwise, then the effective sum has to be zero for the body to be in equilibrium. We have read in our previous lecture, we have seen that by convention, clockwise moment is termed as negative and anti-clockwise moment is termed as positive. This is conventional, and we will use the same convention. Therefore, an alternative statement of principle of moments can be that the sum of clockwise moments on a body should be equal to the sum of anti-clockwise moments on the body for the body to be in equilibrium. We have a fair idea what the principle of moments state. We'll understand it better by jumping into numericals. In this numerical, the problem states that we have a force of 50 Newton from the pivot applied at a distance of 50 centimeters. So this distance is 50 centimeters, and another force of 100 Newton is applied at 10 centimeters from the pivot. So this is 10 centimeters. And the question asks us to find the moment of force. What is the moment of force? We'll find the moment of force for the 50 Newton force first. Moment of force for 50 Newton force is the applied force into the perpendicular distance from the pivot. That would be, since the force is applied in this direction and this is the perpendicular distance then, which is equal to 50 centimeter. Therefore the moment of force will be 50 Newton into 50 centimeter. This is in CGS unit. We will convert it into SI unit. That would be 50 divided by 100 meters. This turns out to be 25 Newton meter, and this moment of force of 25 Newton meter is in anti-clockwise direction. This force is trying to turn the body about this position, about the pivot, in anti-clockwise direction. So we are letting it remain as positive. Similarly, the moment of force due to the 100 Newton force is 100 Newton into 10 centimeter. The equivalent will be 10 divided by 100 meter, and that would turn out as 10 Newton meter. We note here that this 10 Newton meter is again in the clockwise, rather anti-clockwise direction. Therefore, this will also be positive. For the sake of argument, if this force was applied in the opposite direction, then the moment due to that force would be in the clockwise direction, and we would have taken it as negative. Therefore, the total moment of force is equal to 25 plus 10, that is equal to 35 Newton meter, and I will mention here that it is in anti-clockwise direction. Therefore, the answer for this numerical will be the moment of force, effective moment of force is 35 Newton meter. What can we say from this? We can say that the body is going to undergo rotation, and therefore the body will not be in equilibrium. In our next numerical, we will see a scenario in which equilibrium is maintained. Let us see that example now. In this example, the numerical states that there are two kids weighing 15 kg and 20 kg sit at 1 meter and 1.5 meter from the fulcrum of the seesaw, and both of them are sitting on the same side. Numerical asks us, where should a man of 90 kg sit to balance the seesaw? So the seesaw has to be in a balanced state, which means that equilibrium has to be maintained. This is what balanced state means. Therefore, the principle of moment will apply in this question. Now let us picturize what is happening here. There is a seesaw. There is the fulcrum in the middle, and a kid sits here and another kid sits here. This kid is 15 kgs and the other kid is 20 kg. This distance is 1 meter and this distance is 1.5 meter. Now we need to find out where a 90 kg man sits for this to be in equilibrium. Let us do a thought experiment. Suppose that the man sits in the same side of the seesaw as the two kids. What will happen? What will happen is that these two kids are producing a moment in the anti-clockwise direction. They will try to turn the seesaw in this direction, the anti-clockwise direction. And same will happen with the man if he sits on this side of the fulcrum. As a result, there is no possibility of a balance of the seesaw since all the moments are in anti-clockwise direction. Therefore, we can say that the man has to be sitting on the opposite side of the fulcrum. Let us say he sits somewhere here. Now we take the distance as d, the distance from the fulcrum where the man sits as d, and we will find out what the distance d is. Let us first check out what is the total anti-clockwise moment created by the two kids. Total anti-clockwise moment is equal to the first kid weighing 15 kg is sitting at 1 meter from the pivot. So it will be 15 kg into 1 meter, and the second kid of 20 kg is sitting at 1.5 meter from the pivot. So that will be added as 20 into 1.5. This turns out to be 15 plus 30, that is 45 Newton meter. So we get a total anti-clockwise moment due to both the kids as 45 Newton meter. Now in order for the seesaw to be in balance, there has to be a clockwise moment of 45 Newton meter created by the man. Let us write it out. Clockwise moment needed for balancing is 45 Newton meter. But how much moment is actually being created in clockwise direction? Clockwise moment generated, and that will be equal to the weight of the man into this distance d, which is equal to 90 kg into d, that is 90 d Newton meter. I am taking the distance d in meters. Now we know how much clockwise moment is necessary for balance. We have the amount of clockwise moment generated in terms of t. Therefore, for the balance to occur, the 90D will be equal to 45, and that turns out as D is equal to 0.5 meter. Therefore, we see that for the seesaw to be in a state of balance, the man should sit at 50 centimeter or half meter away from the pivot and in the opposite direction than what the kids are sitting. With this example and the previous example, I get to know about the moment of force in a much clearer sense. We can picturize it much better now. And with this example, I conclude today's lecture. In my next lecture, we'll talk about the center of gravity of a body. We'll see different examples of center of gravity, and we'll learn how to find the center of gravity of a body and what exactly the center of gravity means. Till then, have a great day.